Okay, this is the last part on the turbulent boundary layer power law form, that is part 6e. Okay, previously we have obtained the delta, the tau naught, and also the small cf, and then we have another two parameter left, that is the drag force and also the skin friction coefficient, that is the big cf. Okay, so we need to get the FD, the drag force per unit width. So we come with this the integration of the tau naught dx from 0 to the L. Okay, so we know previously this actually the tau naught equation. Okay, so we can write in terms of this tau naught equation. Okay, and we substitute the tau naught into the FD equation here. Okay, previously we know that the tau naught also can express by this equation, so we can just substitute into this FD equation. Okay, so we can get this expression. Okay, so we are going to do the integration with respect to the x. Okay, and from 0 to the L. Okay, we can take out everything that constant, so we just leave in terms of this x here. So that is actually x to the power of 1 over 5, 1 over x to the power of 1 over 5. So we are going to integrate with respect to the x from 0 to the L. Okay, the rest is just the constant, so we just take it out from the integral. Okay, so after we do the integration, we will get this 5 over 4, okay, from this, and this will become the L, 4 over the 5. Okay, because it's actually x 4 over 5. Okay, so we can just rearrange and manipulate the equation. So we can times the constant here, so we'll get this expression. Okay, then we can rearrange our FD. So FD we can just write in terms of this expression. Okay, so if we were to simplify the FD to express in terms of the Reynolds number term, so we can put the multiple the L over L. So this is actually inside this bracket, or if this is actually L the power of 1 over 5 divided by the L power of 1 over 5. So we can just put it here, inside here, so we can rearrange our equation. Okay, and we know that the Reynolds number, so this is related to our REL here over this length of this flat plate. Okay, and then we can just actually rearrange and simplify the equation of the FD into this expression here. Okay, so we can introduce here this one because we want to explain of the Reynolds number. Okay, here we have another L1 over 5, so we can take it out, so it can be multiple with this expression out here, so it can just become the L. So it's just a simple math. So we can get the FD, or the drag force per unit with this expression. So if you know the L, we know we can calculate the Reynolds number. Okay, we given the properties of the fluid, the viscosity, and also the U infinity, so we can get what is actually the FD. Okay, if we know the FD, okay, the drag force related to the flat plate, we can know in terms of the power, okay, that we can get to overcome this friction effect. Okay, so we have know the FD. So later, when we want to calculate the power that we need to overcome this friction effect, so we can use this FD equation. So we will see this in the examples. Okay, after we find the FD, so let's look on the last parameter that we can determine from this for the solution for the turbulent boundary layer. That is the big CF. That is the skin friction coefficient over the length L. So this is actually the known equation previously, related to this flat plate of the length L. So we can just get the coefficient, the drag force divided by the half rho U infinity squared L. Okay, and then we know that previously also this is the expression that we get in terms of the FD, in terms of the Reynolds number. So we just substitute the FD into the CF. Okay, so we can cancel the same term here, the rho U infinity squared, the L, so we can cancel, and then the 2 can times with the 0.036, so it will become 0.072 divided by the RE, Reynolds number over the length, the power of 1 over 5. Okay, so this is the CF value. So we have determined, or we have actually obtained all the parameter relevant to this flat plate for the turbulent boundary layer. So might be when you do the solution, it might be in terms of the rounding of error, might be your constant just a little bit different from the given in the textbook or in the table that I've shown you previously. Okay, but don't worry, if it's just slightly different, maybe like 0.072 or 0.073 is okay. Okay, it's not much different. So maybe just the matter of the rounding of errors. Okay, just a simple the error that we can get from our calculation, okay, using the calculator. So it's okay. So I think we have done on the turbulent boundary layer power law form, where we in this part, part 6, that we use the turbulent velocity profile using a power law profile of 1 over n, that is n equal to the 7. So this is just the same like in the textbook, but like I said, again, in the textbook, they always like to simplify the step. So I've shown you all the steps on how to actually get the relevant parameters. Okay, with that, Assalamualaikum warahmatullahi wabarakatuh, and thank you very much.